Welcome to Aero Engineering 210 Lesson 4. This lesson is about air. In this lesson we will talk about parameters we use to describe air and then introduce some equations and methods we use to manipulate those parameters. These are the lesson outcomes for this lesson. Please hit escape and take a moment to review these outcomes. And then when you're ready to resume, just hit the slideshow button again. We will begin by discussing parameters we call flow properties that describe the state of air. Then we'll introduce the equation of state that relates some of those properties to each other. We'll introduce an equation for the speed of sound and a parameter called Mach number. Then we'll talk in general about dimensionless parameters. Mach number is dimensionless. We'll talk about what in general dimensionless parameters, what value they have to us. And then we'll finish by a discussion of units conversions. So air is described by four fundamental properties. These are point properties, which means they can be different at each point in a flow field. The properties are pressure, density, temperature, and velocity. For pressure, the symbol is a capital P, and the units are pounds per square feet or newtons per square meter. Newtons per square meter, we know, is also given the name pascals. And pressure has the dimensions of force per unit area. Density is given the Greek symbol rho and has units of slugs per cubic foot or kilograms per cubic meter. The density has dimensions of mass per unit volume. Temperature is given the symbol T, capital T, and has units of degrees Fahrenheit, degrees Rankine, degrees Celsius, or Kelvin. Kelvin doesn't have degrees. In general, we use the absolute temperature, degrees Rankine, or Kelvin. And then velocity is given the symbol capital V and has units of feet per second or meters per second and dimensions of distance per unit time. The equation of state is also called the perfect gas law. It relates three of those flow properties to each other according to the equation shown that says that pressure is equal to density times a proportionality constant times the absolute temperature. The proportionality constant R is called the gas constant or the perfect gas constant, and has a value of 1,716 foot-pounds per slug degree Rankine or 287 joules per kilogram Kelvin. The perfect gas law works for gases at moderate temperatures and pressures, and it works for air. And the values of R that were given are for air. There are different values for other types of gases. And the gas that obeys the perfect gas law is called a perfect gas. Speed of sound also describes the state of air. And the speed of sound depends only on a couple of constants for a given gas, and then the temperature, the absolute temperature of that gas. The equation is given there. We use the symbol A for the speed of sound. It has units of feet per second or meters per second and dimensions of distance per unit time. The equation is that the speed of sound is equal to the square root of gamma times R, the same R we used in the perfect gas law, times the absolute temperature. And the gamma is the ratio of specific heats that you probably learned about in chemistry. The specific heat at constant pressure divided by the specific heat at constant volume for a gas. And that value is 1.4 for air. And don't forget to use absolute temperature in this equation and in the perfect gas law. Now we introduce our first dimensionless parameter. This parameter is called Mach number and is given the symbol m. And Mach number is defined as the ratio of a flow velocity to the speed of sound in the air at the same point where the velocity is measured. If this velocity is a local velocity somewhere near a moving body, we call the Mach number based on that a local Mach number. And if the velocity is a free stream velocity far from the body, and we're measuring the relative motion of the air far from the body relative to the body's motion, then we'd call that Mach number based on that free stream velocity, we'd call that Mach number free stream Mach number. Mach number is dimensionless. The dimensions of velocity and the dimensions of the speed of sound are the same, distance per unit time. And if the units are also the same, feet per second for velocity and feet per second for the speed of sound, then when we divide the one by the other, we get the units cancel out and we get this dimensionless parameter. Dimensionless parameters will be very useful to us in this course. They allow us to compare two different situations that have matching values of a dimensionless parameter. So for instance, we might have a wind tunnel test of a model of a full-scale airplane, and then we might also have the actual flight test of that full-scale airplane. If the Mach number is the same in the wind tunnel test and in the full-scale test, then we would expect that some of the phenomena in the test that depend on Mach number, we would expect them to be the same in the full-scale test as in the subscale test. And this can be very useful because we can often use the results of the wind tunnel test to predict what will happen in a full-scale flight test for the same value of Mach number, for instance. Finally, let's talk about units conversions. You recall that in our last lesson we introduced an organized procedure for solving well-defined problems. And we introduced an acronym, GAFASICS, to help us remember the steps in that process. Well, the C in GAFASICS stands for consistent units, and we want to be sure that we know how to convert quantities that are given to us in a well-defined problem so that they are all in consistent units so that the numerical value of our answer will be correct. These units conversions are very simple. You simply multiply by 1. And here's an example. Let's say we have a density specified as 1 kilogram per meter cubed, and we want to express that density in the English engineering system. So we start with SI and we multiply by 1 a few times. We multiply by 1 slug over 14.594 kilograms. When we do that, the units of kilograms will cancel out and we leave us as our unit of mass being slugs. And then we multiply by 1 cubed, 1 meter over 3.28 feet, quantity cubed, and that'll cancel out the meters cubed in the denominator of the original density and leave us with units of feet cubed for our volume in our final expression for density. We multiply that out and get an answer of 0.001942 slugs per cubic feet, and that's equal to, in the SI units, 1 kilogram per meter cubed. Now let's try an example. Here's the example problem. If the density of air is 1 kilogram per meter cubed, then what are the dimensions of a cube containing 1 pound of that air? So let's use Ghafasics to solve this problem. First, we're given that the density is 1 kilogram per meter cubed. We're told to find the dimensions of the cube containing 1 pound of air. And we must assume that the density of that air is uniform, otherwise we can't really work the problem. And also we must assume that the acceleration of gravity is equal to some standard value. We draw a sketch, the S in Ghafasics, and in that sketch we show the cube, we show a dimension of the cube, we give it the symbol D, and we know that since it's a cube, the dimensions are the same in all three directions. And we write down the equations that we'll need to use to solve this problem. First, we're going to use Newton's second law, F equals ma, or in this case, weight is equal to mass times the acceleration of gravity. We need that because the density is given in mass per unit volume, and pounds is a measure of weight. So we're going to have to convert from mass to weight, and that's why we need that acceleration of gravity. We have the definition of density as mass per unit volume, and we're going to give volume the symbol script V. We have not at this point given a symbol for volume, and we don't want to confuse it with the symbol for velocity, so we'll use this script V to keep it distinguishable from velocity. And then we know from geometry that the dimensions of a cube are equal to the cube root of the volume. So first we convert to consistent units. That's the C in Ghafasics. And we did that before. We'll make that conversion again and get our answer in English engineering units. And then we substitute and solve to find out what the mass of a pound of air is. So this substitute and solve, we use the equation that weight is equal to mass times the acceleration of gravity, and we solve it algebraically for the mass in terms of weight and gravity. Mass is equal to the weight divided by the acceleration of gravity. Then we substitute in the values, 1 pound of weight and acceleration of gravity 32.18 feet per second squared, and we calculate that a pound of air has a mass of 0.031 slugs. Then we finish up. We move down the Ghafasics acronym, so we can't see all of it on this slide, but we can see some of what we did before, and we continue working on our problem. We have that density is equal to mass over volume, or volume is equal to mass divided by density. So again, we solve algebraically, and then we substitute and solve for a numerical answer. So the volume is equal to our 0.031 slugs divided by the density, and that gives us an answer of approximately 16 cubic feet. The dimensions of the cube then, our third equation, is just the cube root of the volume. So we take the cube root of 16 cubic feet and we get 2.52 feet. And we box that answer because that's our final answer. Now, we're not done. There's one more S in Ghafasics, and that's the sanity check. So let's think about this. 1 kilogram of air occupies 1 cubic meter. We know from other courses or other knowledge that on Earth, at at sea level, with the acceleration of gravity at sea level on Earth, 1 kilogram weighs 2.2 pounds, so we would expect 1 pound of air to occupy less than half of 1 cubic meter. And sure enough, if we cube 2.52 feet, that will come out to a volume that's less than half of a meter cubed, which is 3.28 feet cubed. Another thing we can do to sanity check our answers to make sure the units came out right. And they did. We got a volume in cubic feet, we took the cube root of that, and we got the dimensions that we were looking for in our final answer in units of feet.